Hello, my name is Nigel Griffiths, or we can Power Systems ATS in Europe. This movie is about the active Systems Optimizer. Now, a little warning here, this is using very advanced technology to do some very advanced tuning. Fortunately, now we have a tool that will go off and do this for you. So what do we need to run ASO? Well, first of all, we have to be at AIX 7, TL1 or above. Don't forget those service packs. And we need to be running POWER7 in POWER7 mode. Some complicated things are allowed, like workload partitions and active memory expansion, but there are a few things that are not allowed if you want ASO to work. AMS is one of those. Paging between LPARs is just too complicated. Enhanced Affinity is nearly always on, so that's not a big issue. And live partition mobility. The problem there is that upsets the system resource affinity domains. It's installed by default with AIX 7 TL1. But be careful, it's not supported on older releases of AIX and the hardware. If it finds itself in those configurations, it just hibernates itself, so it looks like it's running but not actually doing anything. A quick reminder on how to check these things. The OS level -S command will tell you what level of AIX you're running. If you've upgraded to TL1 from TL0, then it's worth checking that you actually have the package installed, and we can use lslpp to do that. And then you need to check the mode of your processor. My quick dodge is using the lsconf command to do that and pick out the right lines of the output. Now, once ASO is activated, it has no other need for user involvement. It just gets on with doing its work behind the covers. It identifies and optimizes the suitable workloads using two sources of data. First of all, the AIX kernel statistics about processes and threads, but it's also pulling information from the POWER7 hardware performance counters that come out of the POWER7 chips. These are very low level counters usually used by kernel developers. It then improves the cache and memory affinity for particular processes, and it does this by dynamically re-evaluating the tuning options for particular workloads and then changing things like the resource sets or the system resource affinity domains, which will move processes and memory around inside the logical partition. It performs pre- and post-optimization monitoring, so it monitors a process for a minute or two before deciding what to do. It makes a change, and then it will monitor to see if it's improved the performance and behavior of the workload. If it says that it can't find any gain by some of its activity, it will back out those changes and then hibernate and wake up later on when it thinks there's a better opportunity for optimization. The AIX kernel process dispatcher makes the decisions about which process will run on which CPU. It needs to do this at very high speed because it wants to maximize the amount of work we're getting through. It uses a simple priority rules and queuing system to do this. It has very limited scope to make more intelligent decisions. This is where the active System Optimizer comes in. It takes this longer term view, looking at the processes and what they're up to and which bits of memory they're accessing, and based on this more historic information, we're talking in a couple of minutes of course, it makes better decisions about where processes would better run. It's going to use the system resource affinity domains and the resource set rules to do this, that then the dispatcher actually operates these rules and queues. ASO is focused on three types of optimization: cache affinity, aggressive cache affinity, and memory affinity, and we'll describe those next. Let's take this first example of cache affinity. In the diagram in here we have two POWER7 chips. They may be on the same system planar, or they may be across the machine in the 770, the KEX, or the 795, the different CPU books. ASO will then be monitoring the processes, and using the hardware performance counters out of the chip, it can spot the level 3 cache latency of moving the cache lines between the two caches between the two chips. If it finds this situation, it then decides it would be a good idea to move some of the threads and processes from the B chip into the A chip. When it does this, it finds that everything sits in just one level 3 cache now, and this gives us a performance boost. Typically it's going to do this using a resource set. In the second case of aggressive cache affinity, similar things are going on where we have lots more cores involved in running a workload, but it still sees a lot of level 3 cache movements, and it decides that the threads running in the POWER7B chip would be better to be moved to the other chip, even though that is fully used, to reduce the amount of cache movement and actually help the performance. So in this case, we actually just move the workload to work on a single chip, avoid the cache movement, and again get better performance. The third optimization is memory affinity. The dispatcher is quite happy to dispatch processes to the first available CPU, but in this case it's given the applications access to POWER7A chip, unaware of the fact that the memory is actually connected to a different chip, so that when it wants to access the memory, it takes a longer path across the machine. If this was transitory, this is no big deal, but if this goes on for a long time, this is working slower than needed. In this case, the optimizer will decide to move the memory from one POWER7 chip to local POWER7 chip, so it now sits with the processes and threads that are accessing it, and this will give us a performance boost. So if you want ASO to start optimizing things, this is the way that it decides. First of all, it really likes multi-threaded workloads, which is very common these days, but it needs to be stable for a period of time because it's going to monitor what it's doing before making decisions. The virtual machine does have to be busy. If it's only running at 10% busy, there's very little point in optimizing that workload. It might as well just let it run. And AIX will be doing things like folding off spare virtual CPUs, for example. It also needs a minimum lifetime. If your applications come and go very quickly, then again it's not going to get the history and not be making optimization recommendations. Also, if you started doing lots of manual tuning, you've locked a process onto particular CPUs, or you start using R sets and things like that, then ASO will assume you know what you're doing and hibernate. You can also mark particular processes as don't bother optimizing these, and then ASO will leave them alone. Okay, then let's get practical. We have to first of all start a kernel service, then there's an optimizing command where we can switch it on. There's some other tuning options. Logging is particularly interesting. We'll have a look at some examples, and there's some fine control with some shell variables. It's a two-stage process to get ASO up and running. First of all, we have to start the kernel service, and we do that with the start src-s for the subsystem ASO, and then we need to activate it so that it actually starts trying to optimize. We use that ASO command, ASO options command, and we have to set active equals 1. If you then go looking for the details with the ps command or nmon, you can see this new process running. I've never actually found it using any CPU time at all. It's using a tiny fraction, less than 0.1 of 1 CPU. It does change the number of threads that it's using as it's tracking various workloads and trying to decide what to do. The ASO command is like the other options commands, VMO for example, and has the same similar configuration details. Don't forget the -op if you want it permanently sent, so that will carry on over a reboot. The -h gives you some information about what the numbers mean. There is also a bunch of restricted options that you can set. Of course, you're not allowed to do those normally unless we've been told to by AIX support. I looked at the names and they give no clues about what they actually do. As it runs, ASO logs to var log ASO. There's two files in here. ASO.log that has just some basic details of whether it's on, off, or hibernating, and then the detail stuff goes into ASO_processes.log. Do be warned though that although it's completely readable ASCII text, and we'll have a look at some examples in a minute, it's not formally documented. So don't go asking questions for export about what these things actually mean in the log files. When I first ran the manual page for the ASO command, I got a little bit confused. It says that you can run ASO outside of the system resource controller, but I'm pretty sure that's only for debugging purposes, so we don't want to do that normally. But the second half includes some shell variables that you can set before you start your applications and your processes running, and this drops hints to ASO about which processes it should try hardest to optimize. Of course, there's a little bit of an oxymoron here that once the app program is running, you decide that you don't want to be optimized. Well, you can't go back and set the shell variable, so you'd have to set these for the next time that you run your applications. The only example I can think of is that if we find out by watching ASO it keeps trying to optimize one particular set of processes and keeps failing, then next time we could tell it ASO options to not try those applications and concentrate on something else. Well, let's start my worked example. We switch it on and we activate it. I start my busy multi-threaded workload, and then I'm going to watch this ASO process.log file. Now remember, it's going to take a few minutes before it starts taking action, so you can't expect things to happen immediately. The log format is not documented, but it is fairly readable. In fact, it's quite nice and chatty. It's almost like listening to the mind of a guru, looking through your system and making recommendations and changes and seeing what happens. Of course, your workloads are very different and you'll see lots of different things happening. This is just an example. I'm actually running this on a POWER7, and I've made sure that the virtual machine is badly laid out across my box. The ref numbers in here is the SRAD name for the two KEX in my machine. The SRADs are the individual POWER7 chips, and you can see I have a mixture of CPU and memory spread across the entire machine. This will give ASO a good opportunity to do better when it's running my workload. And if you look at SRAD 3, we have some memory there on one chip and it actually has no CPUs at all. So this is what the log file looks like. At the top half we see there's a timestamp and the machine and some bits and pieces that I'll remove for readability for the later logs. But immediately you can see that it's been enabled, it's been switched on, and it's now active. It finds that the logical partition is not busy enough to worth trying to tune, so it'll actually go into hibernation. Later on, I've started my parallel worms program that regularly updates the same piece of memory from the different threads. We can see at the top that it's switching on this stability monitor basic, so it's going to check is this running for a long time, and then it switches on the advanced monitor. It then decides later on that it hasn't got enough work, it's not busy enough program to warrant tuning, so it's going to then unconnect those monitors. So later on I try running the ParaWorms with lots more threads, and we see in the logs here it's giving it a further go. It's suggesting using the system resource affinity domains and trying to control the program that way. It then monitors for a bit and it finds that the gain is a negative number, so it actually went slightly slower by doing that, and so it backs out, switches off the monitors again and rethinks it. So now we start up 3 copies of my ParaWorms application using different numbers of threads and different settings. In the middle here we found that it's got 2 SRADs that it's using. If you look at the number of cores and the CPU number and compare that to the ls srad command, you'll see it's neatly splitting those 2 ParaWorms, so it'll actually be running on 2 different chips in 2 different KEX. So that does make a great deal of sense. Then further down, 3/4 of the way down, it's trying to look at the 3rd ParaWorm, the one that has a PID number of 6226514, and it's trying a different strategy for that. It then turns out that it has a gain of 0, so it didn't actually make any difference, and it removes at the bottom the RSet for that particular one. So we can see it coming and going, trying out various strategies for the different programs and deciding whether it works or not. But we'll stop looking at the logs there. Of course it goes on forever tuning and trying different options. Here's my little summary: AIX 7 Tier 1 and POWER7 or above. Fortunately it's largely a set and forget. You can switch this on and just look at the logs now and again to see it's up to things. Advanced tuning, certainly not simple to understand some of these affinity options that it's using. It fortunately uses near 0 CPU when it's running, so it's not going to cost us anything to switch it on, and it gently applies these things, tests that it's actually making an improvement, and where necessary it undoes them, or if the workload changes later on. But it does make it pretty hard to demonstrate because it is so dynamic all the time. Particularly good for complex, real-life, multi-threaded, long-running applications, and it's particularly good because it will move things around inside your logical partition if the logical partition is on the larger machines and spread across the various POWER7 chips. This is the first phase of clever affinity tuning. Of course there's lots more things in planned, including perhaps in the future moving the LPAR around inside your machine for better performance. If you want the full detailed resolution and the other movies, this is the URL to go and look at.